Okay. So what? Let's do today is. So what I'd like to do today is to do just spend a few minutes right at the beginning, kind of highlighting the two important things that I really want you to kind of grasp during this with respect to the electromagnetics. Then we have an instrument here called this is the EM31 instrument, probably the most commonly used instrument for site characterization and for environmental concerns. We're going to talk to you a little bit about this, and then Chris. There's Chris Cool. There you are. Sorry. Chris is going to talk a bit about a project that I don't know. Are there other members here that are working with you?
Yeah.
Okay. Big team. Anyway, Chris is going to talk a little bit about his project, and I think that's a perfect segue into a project that we did a number of years ago on the Expo site. I think there's a lot of similarities, and yeah, and then might talk to you a little bit about other types of sources, transmitters, and receivers that are common that you'll come up against. But anyway, that's the objective. So I first of all just want to kind of briefly recap a couple of the important items here. So the first, there's two kind of parts of this. The first is kind of the EM induction part, whereby we've got some kind of a transmitter and it induces currents into an object down here, let's say a plate, a drum, and that sets up currents in here, and those currents produce another magnetic field that can be measured any place up here. So that's the EM induction part, and for that, these pictures and the lab should kind of reinforce the whole concept about mutual flux and coupling, so that you could, with Lenz's law, understand what directions of currents would be moving in the object, and then what the directions are for the subsequent magnetic fields. And that would actually allow you to sketch out a curve that looks like this if you went over it. So that's an important thing. If you get that, then I think you've got a lot of the basic aspects about electromagnetic induction. The second part of that was that depending upon whether the object is really conductive or just moderately conductive, the response gets put into either the real part or the imaginary part of the signal. So remember that signal that's coming back is a sinusoid, and it's got a bit of a phase delay with respect to the transmitter. And so there's a certain part of that that's in phase with the transmitter, a certain part that's out of phase. And there's a response curve that goes with that shows you if you've got very high values of conductivities or frequencies, that most of the information is going to be in the real part. You've got very low frequencies, more of the information is actually in the imaginary part. And then depending upon where you are, so for instance, if you were up in here, then the real part is larger than the imaginary part. And if you went and you did the sketch, then you'd have exactly the same kind of profile, but the amount of signal is proportioned differently into the real and imaginary parts. Now, why is that important? That's important because this imaginary portion of the signal is actually going to get converted to an apparent conductivity. So it's going to come out on this instrument that this quantity here goes to an apparent conductivity, and that is going to occur so long as the separation between your coils, if this separation is much greater, or sorry, now, if the separation is much less than the skin depth. So the skin depth was that depth into the earth at which the signal falls off by 1 upon E. So this is delta. This is 1 upon E. Okay, so the so here was your concept of, where'd it go? The skin depth sort of falling off was 1 upon E, and here was a formula that you could use. That the skin depth was, this is in meters, we just divide by frequency. So that's all the first, that's all the first part. The second part is that whenever we have a transmitter, then there's going to be a certain amount of signal that goes out. There's going to be a region around here which is sort of in the sensitivity zone of whatever my transmitter is. So that's important to kind of quantify. And under special conditions, when the Earth is really layered, we can actually compute what the sensitivity function is for just a homogeneous Earth. And that sensitivity function looks like this. And what does this say? This axis is normalized depth. So it's the true depth divided by whatever S is. So 1.0 here, if S was 3 meters, then the true depth of this would be 3 meters. For an instrument that is oriented like this, you've got a transmitter and receiver that are flat. The maximum sensitivity is about 0.4. So if I've got a separation here of 3 meters, 0.4, that means that I'm really mostly sensitive to what's happening about a little bit over a meter in depth. So you can see that an instrument that's got fairly small s and a curve that looks like that, you're only going to see down a couple of meters, 3, 4, 5 meters. The sensitivity function depends upon what the orientation of the transmitter is. So if the transmitter is horizontal, then my magnetic field is got one particular orientation inside here, so there's some sensitivity there. That's look like this. If I turn the transmitter on its side, so now instead of the transmitter being like this, it was now like this. So now the magnetic field is kind of going out like this. I'm sensing the Earth entirely differently. So the Earth is going to have a different response. It turns out for that type of transmitter, my response curve looks like this. So I've got different orientations of my transmitter receiver. I get different ways of sensing the Earth. So why might this be important? For the following reason, that the apparent conductivity that you obtain, whether it's 10 millisiemens per meter or whatever, is really the number that is, how you think about it, is sort of the integral of this sensitivity function with respect to whatever conductivity that was there. So the idea is you get a number out here, which is an integral of this kind of a function with sigma at depth. So this is actually what you do in the lab. And the important thing to remember is that this sensitivity function actually gets, it's kind of something that's attached to the instrument itself. So if the instrument goes up, then the sensitivity function stays with it so that the amount that's in the ground, part of the sensitivity function in the ground, is small. So we tried to show that in the lab. Actually, maybe you do that this week. So here's the Earth function, and here is the sensitivity function, and you've got. You can raise the boom up higher or lower, and you can, for different conductivities that structures that you have. So in other words, if the conductivity structure was like this, so it was resistive and then it was conductive, and the sensitivity function looks like this, then the number that you get out is sort of the integral of this product, which looks like this, and it actually turns out to be, in this case, a pretty low number compared to what the conductivity value is of this layer that you have up here. Okay, so this concept of having a sensitivity function such that you get a number out that's sort of the integral of the sensitivity with whatever conductivity you got is really essential from the point of view of trying to get a handle on what's there. And the thing to remember is that that sensitivity function always stays with the instrument. So here's the this EM31. It's got a transmitter. It's got a horizontal transmitter over here, and it's got a receiver that is over here. And you simply, do this without fall over. Somebody said it looks heavy. It's not that heavy if you just lift it up, but it is heavy if you're walking with it for 8 hours. So you simply go around, and there is a data logger that's attached here, and then you just simply walk along like this, and you'll have your lines out in particular direction, and you actually have the option of deciding how you want to collect the data. So you can collect the data with this instrument at shoulder height here, which is usually what happens, and you just simply tend to kind of walk along, and it would give out for you, record for you, both the in phase and the quadrature phase, or the real and imaginary parts of the data. Remember, I said that this apparent conductivity that you get out is the integral of your response function with sigma of zdz, and that this response function stays attached to the instrument. If I have a uniform conductivity of, let's say, sigma naught, let's say it's equal to, I don't know, maybe 0.1 Siemens per meter. If my instrument is right on the ground, I'm going to get an apparent conductivity that's equal to that. If my instrument is up higher, I'm going to gradually get one that is much less. Similarly, if I have a layered space, so if this is sigma 1 and sigma 2, now my sensitivity function, if the system is right on the ground, it would kind of look like this. If my system is up in the air, I still have the same sensitivity function, but really the only thing I'm going to actually get for a number is that integral. You can see that you get different information if I actually took two numbers. If I took one in which the instrument was right on the ground, I'd get something, and that would be averaging whatever layered structure I've got. If I lift it up, I'd be getting a different averaging. So I get different numbers, and you could think that maybe you'd be able to combine those numbers and give you information, about maybe the individual conductivities and that layer thickness. Also, that sensitivity function, if I change the orientation of the coil, looks different. So if my coils are vertical, then I'm most sensitive to what's going on right at the surface and less sensitive to what's going on here. So you can see that I could get different information by doing the following. If I set the instrument right down here on the ground, I'm going to get one reading. Now imagine pulling it up like this, I'm going to get a different reading. I'm sampling the earth differently. If I turn the guy on its side like this, again, it's going to be different. And if I put it down like this, it's different. So I can actually get 4 different numbers. And if I had, let's say, a layer over a half space, this gives me 1 parameter need, another parameter, and a layer thickness. If you have 3 parameters that have 4 numbers, you think, well, I might even be able to do that. So that's the idea of kind of the sensitivities and what the instrument would do. And then as we come along, that quadrature part, the imaginary part, gets converted to an apparent conductivity, and the real part, the in-phase part, gets converted to basically a map. So the units are different. This is actually in conductivity. This is just in units of volts per meter, and it's a different map. The importance of this is it's mostly used for trying to find big conductors or metallic objects. So this is kind of like a metal finder, and this is actually telling you something about the conductivity. Okay, so with that, I want to just sort of introduce very briefly where we want to go, a little bit of a background on this, and then Chris is going to tell a little bit about his project, and then I'll come back to the Expo site. So as I'm sure know, that in Expo in 1986, Vancouver had this great big exposition. This was the time that Vancouver really became on the world map. In the region down, this is false. This is all the False Creek area. This is before anything was built up. Plaza of Nations still exists. Here's Science Center. Everything else was completely void. There was a BC Place Stadium with a different roof, and the whole place was actually quite marvelous. And for 5 months, all the countries of the world were there, and it was just a happening event. And then after that, everything went away, and they decided, okay, we're going to rebuild this area. So that then prompted them to look at what was going on in here, and it turns out to have a very large historic past, and try to make sure that the proper site characterizations were done so that you could go in and you could build all of this complex of buildings. And that's probably a good segue for you. And so I just took what you sent me, made it into 3 slides, and you could use them, just tell a bit what happened, and then we'll pick it up from okay, so just go ahead with this.
Yep, perfect, thank you.
Oh, I love it.
Okay, so by the way, this was not my idea.
No, but so I never look. It was made to happen, right? I never take the bus. I always ride a bicycle. But for some reason or other, last Thursday I had to ride a bus. I got on the bus. First time I'd ever used a compass card, right? So I'm kind of fumbling around, right? And then I get in there and I look. I said, I know this guy, right? He just got on the bus too, right? I said, what are you doing here? And I said, do you have a capstone project? And he said, yeah. I said, well, what are you doing? He said, well, we got this area down by the Expo site that we're trying to do site characterization on. hello, like this sounds pretty good. Yeah, that's so it's meant to happen, right? These things.
So he's never taken the bus, and now I'll never take the bus. All right, so for our capstone project, we've been given a contaminated site in Vancouver, and it's located near the Falls Creek area. It's actually on the south side of the Falls Creek area. It's close to the Olympic Village, so it's similar in terms of what was done prior to the Olympics here in Vancouver, where they just went ahead and reclaimed that entire section here in the south, right between, I guess, Canby Bridge and Main Street. And so we don't exactly know where our site is, but it is, it's about 200 meters up gradient from the shoreline. And the shoreline is located northwest of our site. So we estimate that we'd be, so if it's in that direction, we assume that we're probably in that area down there. Our site is, it's located right here. It's 60 meters by 37 meters, and this general area is about 200 to 300 meters. 300 by 200 meters. We've had a range of industrial and commercial activities in this area over the past 100 to 150 years. On our specific site, which we've been contracted to remediate, there's a film processing laboratory that's still still working, and we've also had a machine shop and welding on that site. In addition, surrounding our site are other businesses and industrial activities that might have led to contamination of our site just because they would have flown down gradient. And these include a salvage yard, also some other automotive.
Dry cleaning operation.
Yeah.
One of the most important ones.
Yeah, dry cleaning, automotive repair, and this has led to us assuming that there might be these potential contaminants on our site. And so we have to look at testing for them and then remediating the site if need be, based on the standards that BC has for contaminated sites, which came into effect after Expo 86. So essentially what pushed for all the standards that we have now today. And so we really didn't look at geophysics per se in terms of how we would test for these contaminants. We assume that they'd be tested for looking at groundwater sampling, soil sampling. But I guess you can explain how the Expo 86 case history, they essentially use geophysics to look for essentially buried petroleum tanks. There was also a former rail way in this area, so they were looking for actual pieces of metal besides just the containers that would have housed any contaminants, pipelines as well. We didn't consider that for our project proposal, but we might actually include it when we actually have a presentation. So yeah, that's about it.
So do you take soil samples then and just test for all of these things?
Yeah. So basically, in our project proposal, we proposed several borehole sites on site and around our site, and that's how we would have tested for any contaminants. Yeah.
So
we're still in the process of looking at the data that we've obtained and figuring out what contaminants are actually on site and which contaminants exceed. So there might be some contaminants, but if they don't exceed the current standards, then we don't have to remediate for them.
Do you know what they're planning to build there?
Yes.
There is a mix of a residential and a commercial building. So when looking at the standards, we had to go in standards based on commercial and industrial use together. So from our knowledge, from our sponsor, we've been provided a certain picture of what's going to be built. since they'd done a similar project and a similar redevelopment on a site before. So they want like a bottom floor would be a commercial zone, while the upper couple floors would be residential. So they want us to remediate in a manner that would be sustainable for the future. Another thing that we've been told is the film laboratory on site has no plans on doing any infrastructure work till 2025. So we've been basing our timeline for remediation and having a complete, or having a plan or a monitoring plan implemented up to that time for now.
Do you know how deep you have a lot of fill there, right? And
Yes.
stuff.
So,
do you have any idea how deep that is?
yeah, so all of this area is historically, water was extended up here and actually all the way up to Clark Drive. And so that has all been infilled with gravel, sand, and you'll see in the case history from Expo 86 that they've also found just like wood trash, and that's obviously complicated. That complicated that case history, and I'm not sure for our case, we haven't yet looked through the data to determine if we would have anything besides fill and just the regular tilt that we would find underneath.
Based on our proposal, we've kind of gone with drilling boreholes up to a depth of about 20 meters. That from our research, it showed us that will enable us to collect, go deep enough to collect enough groundwater samples. So we don't exactly know how deep it is, but from like using Google Earth and stuff, like getting elevation of the ground and stuff, we determined that 20 meters depth would be appropriate to reach the groundwater.
Good. Okay, thank you.
Thank you.
Let's see. Let me go here. Oops, where did my... There we go. So I think there was a lot of things that probably happened there that also happened north of here. This is sort of in the northern part that Chris was talking about. And this line that goes through here is actually where the water used to be. So virtually all of the stuff in sort of the southern end of Falls Creek area has all been infilled. Just about everything you can imagine. So there's gas manufacturing plants in here. There was all those kinds of sawmills. There was electric rail lines that were going through. There were substations there to try to work with transformers. And a lot of those transformers, they had to drain the dielectric fluids out of them. Those contain PCBs. That's the main issue that was what was involved. And it was lots of wood waste because they were just trying to fill things in. So virtually everything that you can imagine was what was done. What prompted all of this, kind of dismay of a lot of people, is that after Expo 86, when they went in to kind of do the site characterization, they do what they usually do. They go and do a couple of trenches, right? So they dug this trench. It was only 10 inches wide or something like that, and a few feet deep. And after a couple of minutes, they started to notice that there was oil that was coming in. And in fact, in some places where they were digging, you could get sort of like a number of liters per minute of this stuff. And at that point, everything basically just shut down, and then they decided that they needed to do something. So this was at the time that we were just getting into environmental geophysics at UBC, and we got kind of excited about what we might possibly do there. And so we thought, well, let's see if we can't go down, take a whole bunch of different geophysical equipment down and see what we can see. But for the first thing that you do with any of this, you try to do some background reading on what the site was like, and we managed to get a few pictures of things that at least showed what was there from a number of early sites. So this was 1902. There was a glazing plant up here. In most everything I'll show you, there's a red outline here. It's 100 meters by 100 meters, so it's a little bit bigger than what you guys are doing. The old water line, this was where water was, so the shoreline was up in here, and there was got a sash and floor factory over here, dry kilns, early 1900s. By the time you get to 1936, things are filled in. They've got a viaduct here. There's a substation here, storage. There's an oil house that's over here, and yeah, a number of things have changed. Far more infrastructure as you get, by the time you get up to 1952, there's lots, these things are all old rail lines. This was a place where they had some of these electric train cars, and they were revamping them here. Of importance to us is that there was an oil house that was sitting in here. And what they would do with these oil houses is they use them to drain these transformers, and they pump the oil someplace and try to kind of clean it up and then do something with it. But there was information about a number of spills that sort of happened in this area. So again, you got storage, you've got plumbers and carpenter shops, electric railway, gas plants. Time to get to 61. Again, things have changed. Still have the oil house, more storage out here, and the gas plants down there. And then by the time you get to 74, we've got BC Hydro in there, which means that you're going to have lots of wires and things like that. And yeah, so everything you can imagine. So lots of things that went on in the initial filling up of this whole region, as Chris was saying. They just took everything they've got, and you've got lots of old woodworks and cement or whatever else. Here's a picture, for instance, of just kind of what the area looked like. It's a great big sort of clawing up the wood, just sort of filling stuff in. So you can imagine that everything is there. And here is a slightly expanded area of what was going on at the time, and this is the region that we're interested in. Here's the viaduct over here. When they dug the first hole, or they did the trenching was up in here, and here's where they found the oil that was coming in. Subsequent to that, they've kind of determined that maybe this region in here was kind of oil contaminated. The oil seems to float on top of the water, and then the water table goes up and down, but it's usually like 1 to 3 meters in depth. And it was the soil that was in that fluctuating water table that seemed to be the most contaminated. And it also meant that there wasn't a really distinct interface between where oil might be and where the soil or the water might be. It was more like a three-phase system, and that can, sort of complicate things too. The thing that we look for when we do geophysics is, and all the time when we've been doing this in the class, right? We do seismic refraction, and we say, oh, well, we got a nice dipping layer, or maybe it kind of goes like this. We got a velocity 1, velocity 2, and try to find the layer. The same is true with electrical conductivity. We've got growing on the surface, and then there's a little, something that's buried, or you've got a nice layered structure. Things are kind of simple. When you look to see what's happening in a cross section at the Expo site, however, you see, well, things are really much more complicated, and that's actually, I think, probably very similar to what's going on at Chris's place. This is a vertical cross section. From the bottom, we've got the till layer. So at this point, we're fine. And then we gradually go up. The surface has got fill. This material up here is just, here's where your, everything from cement slabs to wood products to virtually everything that you can think about is sort of up in this region in here. And then you've got a clay silt under here, so that's natural. And then we've got the till. From the point of view of site characterization and stability, it's really the depth to the till that's important. So we thought, well, maybe we could find that. It kind of looks a little bit maybe like this, but things are never quite as simple as you might think. The top part, for instance, actually turned out not to be simple at all. The top, good half meter, close to a meter, was actually filled with 2 layers of concrete. So that had been paved over at one point, and then somebody put some dirt over top, and then they ended up paving again. So we were trying to put holes in the ground just to get energy, trying to put electrical currents in. And remember sitting out there with drills and trying to drill a hole through this stuff, and it was totally impenetrable. So not only that, but that having a sort of cement slabs up at the top can really throw kiboshes into things. So the point about that is that some of these places are just really complicated, and this is what happened here. When we initially thought about doing this, we had a whole bunch of potential surveys that we could do. So for instance, for finding the fill, maybe I should go back and do that. Okay, so for finding this guy here, so the depth of the till, we thought, well, there should be both a velocity contrast across here, as well as maybe a conductivity contrast. So we were trying to do that. So we did a seismic refraction across here on the line. It took actually a fair while, but we managed to get some data. GPR we did. We did something called VLF, which I haven't talked about. I might get an opportunity to talk a little bit more about. That's sort of a natural, it's an electromagnetic frequency domain system that is given up by these big antennas for communicating with submarines. So that's sort of the energy source. So this is an EM experiment. And we did gravity. And we tried to do a magnetics experiment. But the magnetometer that you had on the beach, this proton precession magnetometer, we took that out. We thought, well, that would be great. We'll use that. Turned out that we couldn't use that at all. And the reason for that is that magnetometer only works if the gradients are not too large. And there was so much metal and stuff down there that the magnetic field was changing hugely, and it caused the magnetometer to produce poor results. In the case history on the GPG, there is a gradient magnetometer, and that provided some information. And yeah, then we tried a DC resistivity, which we haven't seen yet, but you'll see next week. And that basically failed because we couldn't get energy into the ground because of all of these cement slabs. So the point about that was that, okay, you've got a background here that you might be able to get, make some distinction. In particular, the object was to try to find the tilt. And there's a whole bunch of techniques. Which one to use? And potentially a lot of these are possible, but some work better than others and are more useful. And it turned out that the oldest technology that exists is in this guy here, this EM31. And didn't even come onto our radar scope until close to the end of, well, of our planning of this, just because we thought, well, it's just too simple an instrument. It's just not going to, it's not going to do the kind of thing that we're going to do. We're going to do 3D stuff here, right? But in the end, this guy was the most, probably produced the most useful data. And you've seen this picture before, but I've got some few more things to talk about. What we're looking at here is, so now you imagine so it's 100 meters by 100 meters. We made lines that look like this, and we walked them here. So this is north, south. And so when we're doing that, the boom is in this direction, and we're walking, back and forth like this. So we go up here, down here, up here, down here. That produced this particular apparent conductivity, and this particular, whoops, this conductivity here, and this sort of metal part, the in-phase part. So what we can see from here is, as we're going along, when you look at this kind of a system, here's some. Let's suppose you just sort of go across on here, and then what do you see? You're coming along there, and it's red is positive, and blue is negative. And as you come across here, so you tended to see this sort of characteristic signature, which is indicative of some kind of object that is in that direction, and you're going perpendicular to it. The same is true over here. You can see again sort of like there's a positive, and then there's a negative and a positive. So that kind of characteristic signature is actually seen right in here. And because you understand how this EM31 works, you might think, oh, no, there's something there that is worth investigating. So just by simply looking at the signatures here and the patterns, you get the idea that there might be maybe some kind of a conductor that's coming up through here, and maybe something that's through there. So that's first thing. The other is we could walk in a different direction. So instead of having the north-south, we could go east-west. And that, of course, excites things in a different manner. And if you look at this picture versus this, so this is north-south, that's the east-west. This is just kind of smoothed out, and it's just some kind of a positive. That's the same. That's what you'd expect if you had a conductor that was going in here, and you're walking this way parallel to it, then you're kind of always at that constant distance from the conductor, and you tend to get things that are elongated like this. So you get a different type of signal, whether you're walking parallel to the object or whether you're walking over top of it. The other thing that was important here, so was the depth of the till, which I don't think we were very successful at. The thing that we were more successful with was looking at the conductivity and trying to find where the hydrocarbon might be. So the thing about oil is that it's resistive. On this apparent conductivity plot up here, you can see that there's this blue region up here, very blue, and that indicates that we've got very low apparent conductivities. And when they did the test hole, that test hole was done right up in this region in here, and that's where the oil was. So our idea was that we'd be able to kind of look at where this contaminating or low resistivity region was in this region up here, and kind of compare that with what was obtained from drilling. And for that reason, we kind of outlined a region out here where the oil contaminant was. Importantly for that, now what we're trying to do is not find an object, but we're actually trying to characterize, an Earth that is, more or less uniform horizontally with respect to this contaminant. And one way that you can make some assessment of that is to orient the boom in two different directions. If I have it north-south or east-west, and I get the same apparent conductivity, then I can be thinking, well, things are pretty uniform in here. And so I'm starting to think, well, maybe that's a good estimate for what that apparent conductivity is. Which is different than here, of course, right? So here, if I've got the boom oriented north-south or east-west, I get very different numbers. So that's telling us, like, wait a minute, things are really changing. It's very dependent upon the boom orientation. But if it doesn't depend upon the boom orientation, then things are likely more just one-dimensional. The other thing that comes out of here, and we look on these in-phase maps, we get very large negative values in certain places. And those are indicative of really high conductivities and probably metal. And in fact, if you kind of look at these maps and just circle the places where you've got these extreme values, and you say, well, that's probably metal, you've been pretty close to that. So at the end of the day, we end up with the following. There's some conductors that are coming in here. We still don't know whether those whether those are pipes or wires. I think they're pipes. So there's some pipes that are coming in here. There's some kind of metallic oil drum here. That was a metal. There's a region up in here, hydrocarbon. So you put the instrument this way, you get apparent conductivities that are pretty similar to hydrocarbons. There's stuff that's coming in here that is very conductive. We were actually pretty excited about this at one point. We thought that it was just such a huge anomaly and was so distinctive with respect to a couple of other things too that trying to figure out what it was, we dug back through some of the literature, and we found that one of the locomotives that used to be in Vancouver had got lost at one point, and we started to concoct a story that maybe it was actually used here for fill, which actually was not so unreasonable. And so that this region here became known as the locomotive anomaly for a couple of years. We eventually, when they did dig everything up, they found that it was concrete with massive rebar. I've never seen rebar that's that thick. It was probably 1.25 inches thick, and just tons of these things. So I'm not sure what they were trying to reinforce, but a lot of this stuff in here was eventually explained by that. And there's metallic objects down in this corner here, which were dug up. So I guess the thing that just wanted to kind of recap with this is a couple of things. first of all, you have a site like yours, and there's a few things that you might try to really identify, and if you can think that there's really strong physical property contrasts between a layer or an interface, then there's a perhaps a good chance that you can find that. If things are just a mishmash, then they're really difficult to get much out of. At the same time, sometimes just a quick diagnostic through with a piece of geophysical equipment can actually tell you a huge amount of material, right? So you get these two maps, which you can acquire these in a day, and you start to find locations of conductors. You can find wires, and if you've got any indication that this may have been a hydrocarbon here, you'd have been able to to do that. So really, of all of the techniques that we used for this, this EM31 was essentially the most effective. Okay. So the plan is that we'll have a TBL Wednesday, and then quiz on Friday. So at the quiz, there's nothing really else that we have to cover in here, but I would like to talk just a little bit about a couple of other transmitters and receivers, different kinds of surveys that you might come across, and then that will finish up the EM, and then we'll start the DC resistivity.